Okay guys, how's it going? This is the second video regarding kinetics and the rates of reactions. Let's take a look at a couple multiple choice problems because these problems are asked in a much different manner and require a better conceptual knowledge than the previous question did, which was kind of plug and chug. So let's double check and make sure that our foundation is strong. So let's take a look at number 3. So write a balanced reaction for which the following rate relationships are true. And let's remind ourselves of a couple of things. So the fractions that we see in front of these compounds that we see here, if we invert those fractions, then that represents the coefficients in the balanced chemical equation. So that would mean then in our multiple choice section that these coefficients like this 2 and 4, for example, better match up in terms of, you know, otherwise it's not going to be the correct answer. So, but that's not the only thing. We also learned an additional fact, and that was that if we keep track of the sign of the fraction in front of the compound, if it's a negative, that tells us that that particular element is a reactant. So, and that was because we added that negative in there to offset the decreasing concentration in the initial problem, because the actual thing is a delta represents final minus initial, and in a normal chemical equation our reactant concentration is going to decrease over time, meaning our final concentration will be less than what our initial was, which would yield a negative number. Now that negative on the outside offsets that and we're left with a positive value. So just some review from the previous video. Now, so that means we have a couple of criteria we need to satisfy. The first is that the N2O5 needs to be the only reactant. And we know this because if we look, it's the only one that has a negative on it. Now, this is pretty interesting because it's not declared at any point that the negative needs to be, or all the reactants need to be first in this rate equation. All this thing says is that they're equal. So you could be on alert that the negative could have been found here on this oxygen like that, out of place, and there could have been a positive value like this 1/4 in between it. What really matters is the sign, and that tells you if it's a reactant or a product. So let's look for the different options that we have here that satisfy the criteria. I should have an N2O5 that's a reactant with a coefficient of 2. So let's look at that. So we only really have two options then. That would be this option here and this option here. So let's take a look at the remaining. Well, then NO2 should have a coefficient of 4. And because the C option does not have that, then that leads us to believe that the correct answer must be A in this case. So A is going to be our correct answer. I hope that was helpful, because this is a pretty interesting problem, and I think that, yeah, once you see it, it's fairly easy. But even myself, I overlooked the fact that this was a negative in front of the N2O5, which demonstrates that it's a reactant. So just be wary of that going further. So let's do the next one. So given the following balanced equation, determine the rate of the reaction with respect to NaCl. If the rate of Cl2 loss is 4.84 times 10 to the negative 2 molar per second, what is the rate of formation of NaCl? So we're going to use some more strategies that we learned in the previous section of the, in part 1 of our videos, and that was that we can create a rate equation based off of this balanced equation that we see here. And another tip, be aware, make sure that your equation is balanced. Is the equation balanced? If it's not, then we can't formate our overall rate equation. So just do an extra sanity check before you continue this, just to double check that the equation itself is balanced, which it is in this particular case, so we're just fine. So let's construct our rate equation. So that's rate equals, well, we have two reactants which are going to have a negative rate delta equation, whatever you want to call it. So that's going to be negative 1/2 delta concentration of NO over delta T. and that's going to be equal to, we have no coefficient in front of Cl2, so there's no fraction in front of it. It is going to be negative, however. That's going to be Cl2 over delta T. Got to put the delta there. And our final one is going to be a positive value because we have a product with a fraction in front of it, 1/2, the delta NOCl. Let me fix that. Over delta T. Now we're going to be solving, because we were given the rate of loss of Cl2, which is right here, we're solving with the rate of formation of NOCl, which is on the right side right here. So I actually don't really care about the NO in this particular case, so I'm just going to erase it for simplicity and move a couple things over. So let's move that over, more space. Great. So, like before, in the previous problem, we're solving for the rate of formation of a product over here on the right side. So what we're going to do is isolate just the delta part of this equation here by multiplying by 2/1 by the reciprocal on this side. And when we do that, we're left with a new equation, which is 2 times, or negative 2 times, Cl2 over delta T, I'll put delta here, is equal to the delta NOCl over delta T. So really all this is saying is that we should multiply the rate of formation, or rather the rate of loss of our Cl2 by 2, and we'll be able to determine the rate of formation of NOCl. And remember that this negative will cancel out with the delta Cl2, so we don't really need to worry about it too much. So it's there just as, well, I keep reminding you guys of it because it becomes important in some problems, but in this particular case, you can see that all your answers are positive. So you can kind of just drop the negative and just plug in the actual value you should plug in. So it looks like if you multiply 4.84 times 2, you should get something that looks kind of like 9.68 times 10 to the negative 2. So our answer is going to be D in this case. That's 9.68 times 10 to the negative 2 molar per second. And that's the rate of formation of NOCl with respect to time, as we see here. So a couple applications for this particular aspect of kinetics. I hope they were helpful. I encourage you to look in your textbook and in the various review sheets on profpaz.com, so you can get more exposure to these type of problems. They're very simple once you get the hang of them, but because they are so easy, many people do not study them as much as they should, and they end up getting dinged on them on the exams as a result. So I encourage you to, once again, look at them in great detail and understand the concepts, because you may not see a problem that looks like the ones I have shown you today. That being said, if you have a conceptual understanding of the material, I can ask you any different variation of these problems and you should be able to solve them. So I hope these videos were helpful, and we'll see you in the next one.